All right, so in trigonometry, we spend a ton of time on sine, cosine, and tangent, right? But today, we're going to pull back the curtain on cotangent. Tangent's often overlooked, but super interesting sibling. By the end of this, you'll see exactly how it works, how to graph it, and yeah, even how it can tell time. Okay, so here's the game plan. We're going to start by linking cotangent to its more famous twin, tangent. Then we'll dive into what makes it unique, walk through a couple of graphing examples, and I'll point out one common mistake you really want to avoid. And you're definitely going to want to stick around for the end, because we're going to connect all this abstract math to something super cool, a sundial. You know, the best way to really get a handle on something new is to connect it to something you already get. So we're going to start with tangent, a function you've probably wrestled with a bit already, and see how it's basically the key to understanding cotangent. And here is the big idea for today. If you understand tangents, you are literally halfway to understanding cotangent. They're like two sides of the same coin, and that's what we're going to call them throughout this whole explainer, opposite twins. So what is cotangent officially? Well, it's just the reciprocal of the tangent function. That's it. While tangent is sine divided by cosine, cotangent is just flipped, cosine divided by sine. And that one tiny flip, believe it or not, that's the key to everything that follows. And check this out. Side by side, you can really see it. They are literally just inverted fractions. That one simple flip in their DNA is what causes all the fascinating differences we're about to see in their graphs. Okay, so what does that actually do to the graph? How does this flip play out visually? Let's break down the key features. We're talking about the period, the asymptotes, where it crosses the x-axis, and its overall shape. Now, before we get into the weeds, if you remember one thing from all of this, let it be this. Because their formulas are flipped, their graphs are too. Where tangent has a 0, cotangent has a vertical asymptote, a break in the graph. And where cotangent has a 0, tangent has an asymptote. They are perfectly, beautifully swapped. All right, this table really breaks it all down for us. So the period, it's still pi, just like tangent. No surprises there. But here's where it gets interesting. Look at the asymptotes, those breaks in the graph. They happen wherever sine of x equals 0. And the zeros, they happen where cosine of x is 0. And check out the behavior. Unlike tangent, which is always climbing, cotangent is always decreasing. This visual just hits it home, right? It's that opposite twin idea in action. Tangent, always climbing up. Cotangent, always sliding down. Tangent breaks where cosine is 0. Cotangent breaks where sine is 0. It's a perfect mirror image. All right, enough theory. Let's actually put this into practice. The best way to really get these rules is to see them in action. So we're going to walk through a couple of examples, from the basics to one with a little twist. Okay, let's start with a nice foundational problem. We've got the basic cotangent function, y equals cot x. And all we need to do is find its vertical asymptotes between 0 and 2 pi. Simple question, where does this graph break? You know, the process here is actually pretty straightforward. It all comes down to remembering one thing. Asymptotes happen when the denominator of your fraction equals 0. For cotangent, that's sine x. So the question really is, when is sine x equal to 0? Well, if you picture the unit circle, that happens at 0, at pi, and again at 2 pi. And boom, there's our answer. The asymptotes, those vertical breaks in the graph, are at x equals 0, pi, and 2 pi. Okay, time to level up a bit. So, what happens when we throw a little curveball in there, like putting a 3 inside the function? This changes the period and the asymptotes, so we need to find both for the interval from 0 to pi. Okay, let's break it down. First up, the period. You take the original period, which is pi, and you divide it by whatever that number inside is, in our case 3. So the new period is pi over 3, easy enough. Now for the asymptotes. The trick is to take the entire inside part, the 3x, and set that equal to the old rule for asymptotes, n times pi. Then you just solve for x, which gives us n times pi over 3. Now we just plug in whole numbers for n, 0, 1, 2, 3, and see which ones fall in our interval. And just like that, we've got our answer. The period is now a much shorter pi over 3, and our asymptotes are at 0, pi over 3, 2 pi over 3, and pi. I mean, think about what that means. We've squeezed that graph so much that 3 whole cycles now fit where just 1 used to. Okay, quick timeout. Before we go any further, I want to talk about the #1 mistake people make with these two functions. Seriously, getting this right will save you so many points on a test. All right, listen up. because this is it. It is so easy to mix up the asymptotes. Just burn this into your brain. Cotangent is cos of x over sine of x. The asymptotes are always where the bottom of the fraction is 0. So for cotangent, that's where sine is 0. For tangent, it's where cosine is 0. It always comes back to the denominator. So at this point, you might be thinking, okay, this is neat and all, but am I ever going to use this? Well, you might be surprised. It turns out cotangent has this beautiful, ancient connection to telling time. This is so cool. It turns out the length of the shadow cast by a sundial is directly proportional to the cotangent of the sun's angle in the sky. As that angle, theta, changes throughout the day, the shadow's length perfectly traces out a cotangent curve. And this is where it all clicks. Think about it. When the sun is high overhead around noon, the angle is close to 90 degrees, and the shadow's super short. That's like the 0 on your cotangent graph. But what about sunrise or sunset? The sun is low on the horizon, the angle is almost 0, and that shadow gets crazy long, right? It stretches out toward infinity. Well, guess what? That is your asymptote. It's not just some abstract line on a graph. It's the shadow at dawn. So look, if you walk away with just one thing today, make it this. Cotangent is cangent's opposite twin. Their behaviors are flipped, and most importantly, their zeros and their asymptotes are swapped. If you can understand one, you've got the key to understanding the other. So I'll leave you with this question. We just connected an asymptote, a totally abstract math concept, to the very real shadow of a sundial. It kind of makes you look at the world a little differently, doesn't it? Now that you've seen this, what other hidden math patterns can you spot out there?